first of our functions is the linear function, and it has a standard form of y equals mx plus c. M tells us the gradient, and c the y-intercept. So we can adjust this gradient, we can make it negative, going downhill as we look at it left to right, and we can adjust the y-intercept. Remember, domain is how far left and right the graph goes, the x values that can take as inputs. Range is how far up and down the graph goes, the y values that can take as inputs. Typically, our domain and range are both x and element of the real numbers. However, just be aware, if we make the gradient equal to 0, we actually get a horizontal line. And now the range is just y equals whatever that value is, y equals 2. Right. A non-function that we're just going to quickly talk about here is a vertical line, and that has an equation of x equals something. Right, but we don't talk about domain and range for non-functions. Okay, so that's the straight line function, really quite simple. Okay, next up is the quadratic function, the parabola, right, and there's quite a lot going on here. The standard form is ax squared plus bx plus c, and people always want to know what do these various things do. Right, well, basically a is probably the simplest one to describe. It just tells us about the sort of steepness of the parabola. And also, obviously, if a is negative, the thing reflects over the axis, and we get what we sometimes call a kind of a sad parabola, actually a concave down parabola, but never mind, we'll call it a sad parabola for now, or a happy parabola. Okay, so there it is. Note the domain, x can be anything. The range is totally determined by the turning point of the parabola, and we'll talk more about that just now. Right, so that's what a does. What C will do is it will pick the graph up or down, and it gives us the y-intercept, in fact, of the graph. Alright? And then people always want to know, well, what does B do? Well, B on its own actually doesn't do anything particularly significant, but B in conjunction with A tells us about the axis of symmetry. So at the moment, the axis of symmetry, remember the formula for the axis of symmetry, x equals minus b over 2a. Alright, at the moment the axis of symmetry is on the y-axis, the line x equals 0, but you'll notice that if we move across, we can see the axis of symmetry changing. Alright, so that's our b value, but notice that our a value also affects our axis of symmetry. So the b and the a value in conjunction affect the axis of symmetry. Notice our domain and our range changing there. And obviously we can move this graph kind of wherever we like. At the moment, we turn off the axis of symmetry. At the moment, there are various intercepts with the axes. Remember, we find x-intercepts by letting y be 0 and y-intercepts by letting x be 0. The other important little thing is what we call delta, which is b squared minus 4ac. Delta tells us about the nature of the roots of the equation when f of x equals 0, when y equals 0. Right, and at the moment delta is bigger than 0 and we've got 2 roots. Notice that if we pick this graph up, alright, delta goes to negative and we have no roots. Okay, if we put all these back to kind of, let's go with something like 1x squared, and let's put that to 0 and to 0, and let's put this to minus 4. So x squared minus 4, right? Notice that x squared minus 4, our delta will be a perfect square. So I'm struggling to get that to minus 4. Our delta is a perfect square because we've got unequal rational roots. Remember that when delta is 0, we have equal roots. In other words, only one root. Okay, and then we can see it. Okay, so that's the quadratic function. Okay, we're going to talk a little bit more about the quadratic function because we're now going to look at it in an alternate form. Alright, and that's in the form where we can, some people call this the turning point form. We get from the standard form to this form by completing the square, and that's a really important skill. But let's just have a look now. So we've basically got our a value as before, and that just tells us how tight or steep the graph is and whether it's kind of happy or sad. Let's put that back to 1. Alright, then the vertical shift and the horizontal shift. If we add a number at the back, alright, this function, if we add a number at the back, the function moves up, and if we subtract a number, the function moves down. Right, if we add to our x values before squaring, the function moves off to the left, right, and if we subtract, then it moves off to the right. Okay, right, notice that our domain and range, at the moment, the domain always x and elementary reals. The range we can see, but if I change the vertical shift, you'll see the range adjusting accordingly. The range adjusting according to the y value of the turning point. Alright, and obviously if a is negative, then the range turns to y less than or equal to the turning point. Okay, right, so it all makes sense. It always makes sense. Right, then just to show the axis of symmetry, that's obviously that line there that goes through the x value of the turning point. And again, we can show delta, our discriminant. At the moment, we have got nice rational roots, so I'm expecting delta to be a perfect square, and there it is, it's 4. Notice that if I pick this graph up, the delta is bigger than 0. If I drop it down, I'll get to a point where delta equals 0, and that's where I only have one root. And if I drop it further down, delta will become negative because I've got no roots. Remember, the roots are the x-intercepts. Okay, the next one we want to look at is the hyperbolic function. It has a fraction and it has x on the denominator, k over x. First up, what k does, it just tells us kind of how far away this thing is from the origin. Okay, but if k is negative, the thing flicks over into the opposite quadrant. Okay, so for example, if k is negative 16, so we can get to negative 16. Exactly. All right, there it is. Okay. Now the reason it's in those two quadrants is that, remember, y is k over x, so x times y is k. Right? If k is negative, then we need a positive x with a negative y, which happens in this quadrant in quadrant 4, or a negative x with a positive y, which happens in quadrant 2. If k is positive, let's just make k, say, let's make k positive 16. If k is positive, then we need either both x and y to be positive, which happens in quadrant 1, or both of them to be negative, which happens in quadrant 3. Okay, we have a domain x not equal to 0 and a range y not equal to 0. Right? We also have these points which are called salient points, which are the points that are closest to the point of intersection of the asymptotes. All right? This graph has got two asymptotes, x equals 0 and y equals 0. Right? They're a little hard to see at the moment, but if we were to shift the graph, okay, so if we were, for example, to shift it left 2 by adding 2, right, to the x, and maybe 3 up by adding 3 at the end, alright, notice the equation, 16 over x plus 2 plus 3. What we'll now see is we'll see these asymptotes at x equals minus 2 and y equals 3. And those are the asymptotes. The domain is the opposite of that. X can't be negative 2 and range y can't be 3. Right. We also have, for this graph, we now obviously have intercepts with the axes, which we wouldn't have before we moved it. Remember, we find y-intercepts by letting x be naught and x-intercepts by letting y be naught. Right, this graph also has, and I'm just going to put it kind of back to its sort of vanilla flavor. This graph also has what we call axes of symmetry. They're lines around which the graph is symmetrical. There's two of them. One is the line y equals x, and the other one y equals minus x. Right, now you'll notice that they go through the point of intersection of the asymptotes. Alright, so it's easy to find their equations because if we move this thing, say 1 to the left and say 3 down, right, those lines are also moving 1 to the left and 3 down, those asymptotes, okay? However, the easier way of probably doing it is just to say gradient of 1 or a gradient of minus 1 and passing through this point, the interception of the asymptotes. In other words, in this case, passing through negative 1, 3. Right, so we need to be able to find all of those points. Likewise, these salient points, they move with the graph. So at the moment, in their vanilla form, let's just go back to 0 and back to 0. Right, in the vanilla form, they are just equal to the square root of k, and negative square root of k, negative square root of k. Obviously, if k is negative, let's just go to say minus 9. Alright, now you'll see that at minus 3, 3, and 3 minus 3. If we were to move the graph 3 to the right, okay, by making the horizontal shift negative 3, alright, then both these points will move 3 to the right. So they'll become 0, 3, and 6, negative 3. Let's just show you that. There they are. Okay. And obviously, if you were to drop this graph down, now those points would also move down. Let's just drop it down by 1. They'd go to 0, 2, and 6, negative 4. Okay, and there they are. Okay, our last function that we're going to look at is the exponential function, and its sort of standard form is y equals ab to the x, all right? B is the base, all right? And if the base is bigger than 1, the graph goes uphill. The base is not allowed to be negative or 0, all right? The base is also not allowed to be 1. If the base is less than 1, we'll notice that the graph goes downhill. All right. Okay, now, for any given base, all right, we also can have a multiplier at the front here. What this is actually doing, it's actually moving the graph left or right, and we can explain why that is the case, all right? But also, if A is negative, all right, then in fact the graph will reflect over the axis. All right, so just be careful, because this is an exponential graph with a base bigger than 1, but it's going downhill. And the reason it's going downhill, the base was bigger than 1, so it was going uphill, but now it's been reflected, and so it's going downhill. Right, notice the domain, x can be anything, always. The range is going to depend on whether the graph's been shifted or not. If I was to pick this graph up a bit by, say, adding 2.5 at the back, all right, now notice the range is less than 2.5. Exponential graphs have got asymptotes, all right, so there it is, there's the horizontal asymptote, and that's just our kind of c value. You can see the asymptote changing. Right, let's just put this back to a base bigger than 1. Yeah, so a base bigger than 1 and like that. And now we can see our vertical shift quite clearly. Once again, we can have intercepts of the axes. We find y intercepts by letting x be 0, and we find x intercepts by letting y be 0. Okay, I hope this short little video has helped your understanding of the 4 functions, their parameters, and what effect they take.